What is a GM tube? Okay, look at the picture. This is the internal structure of the GM tube. Look at the circuit first. Okay, the circuit. Now, you see the circuit, right? It is disconnected initially. Okay, we have positive electrode and we have negative electrode. You can see the two electrodes. This one, the positive electrode at the center, is not connected to the negative electrode at the side. So the circuit here is disconnected, meaning that there's no current flowing in the circuit. Now the circuit is connected to very high voltage, 450 volt here. Okay, but no current is flowing in it yet. Right, now the main components, we have a scale meter here. What is a scale meter? A scale meter is like they count the number of emission of the radioactive source. Okay, later I'll talk more about the scale meter. It's like for every one emission, right, they can count. Automatically, they count it, okay, because when the radioactive emission is emitted, right, they are emitted at very high emission, okay, many emissions, like in just 1 minute. It's like a few thousands for source that are very radioactive, okay? They can emit up to few thousands of emissions in 1 minute. So that is why we need a scale meter or a rate meter to help us to count how many emissions in that 1 minute. Okay, if you remember, radioactivity is the emission of alpha, beta, and gamma, right? And we don't know when will it emit. It's a spontaneous process, right? We don't know when, okay? So sometimes you will see that they use speaker instead of scale meter. Sometimes they will use speaker here. Okay, why do you use speaker? Speaker, we can hear the sound of the emission. If you change it to speaker, then you can hear the emission. It's like, it sounds like tak, 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 something like that. Okay, you can hear it and then you can count it. So they use speaker normally for low emission. So low emission, if only like 5 emission per 1 minute, then you can count it. If you're talking about thousands emission per minute, then you cannot count it. You have to use a rate meter, okay, or a scale meter. So a meter is used here. And then look at okay, what is inside the tube here? This is the tube of the GM tube. The main component is actually this thing. Okay, this thing is the one that detects the radioactive sources. Now, inside, you have gases. What type of gas is inside? They are inert gases. Inert gases that do not react. So it's like the helium, argon, neon. Okay, neon and argon gases are kept inside the tube. They are gases at low pressure. Okay, and then one thing is very important. Often they will ask is that this one, mica window. What is this? A thin mica window. This thin mica window is to prevent the gas from coming out. Okay, prevent gas from coming out. And at the same time, the mica window, it allows the radioactive emission to enter into the tube. Okay, so the radioactive emission can pass through the mica window, but the gases cannot come out. Right, so the mica window is like a thin sheet made of mica, okay, silicon. Okay, and then we have 2 electrodes. The positive electrode, the center, we call it the central wire. This one, central wire. At the center, we have positive electrode, meaning that it's positively charged. Okay, you can see it's connected to the positive terminal. And then we have at the side are the negative electrodes, and it's made of aluminum. Why is it made of aluminum? Because aluminum can prevent alpha and beta from passing, right? So the alpha and beta, right, they cannot come out from the tube. One, it is inside. Okay, so alpha, you can use a piece of paper to block it, but beta, you use aluminium, right? You use aluminium or perspex, you can block it. So these two are to prevent the alpha and beta to come out. That's why it's made of aluminium tube. Okay, now it is negatively charged. Okay, so the sides are negatively charged. Okay, how it works. Now we look at how the GM tube detect radioactive substances. So when you have a radioactive source, this is your radioactive source. It can be a rock or any radioactive material, uranium. Okay, even rock is also radioactive. Later I'll talk about more about it. Okay, so you have a radioactive source here, and you point the tube towards the radioactive source. Okay, you point it towards the radioactive source, and what happens is that when the radioactive give out radiation, then the radiation can be either in alpha, beta, or gamma, right? Or it could be three at the same time. Okay, they enter this tube, and what happened? Now, let's say alpha is emitted. Let's say, okay, so the alpha enter the tube, and the alpha, it can ionize the gas inside. Ionize means that they make the gas molecule inside become ion. Okay, so become ion, then what happens is that these electrode will then attract the ions. Okay, once it ionizes, it's like they knock the electron off the molecule, then the molecule become positively charged. And then that molecule become an ion, right? From atom become an ion, positively charged ion. And what happened to the ion is it will get attracted to the negative electrode. Okay, you can see from the diagram, all the positive charged ions, they move to the negative electrodes, and all the negative charged particles, they move to the positive electrode, the central wire. This happens when there's one emission. Okay, when alpha enter, then straight away the charged particle move to the electrode. Okay, it happened very fast. The alpha goes in, it ionizes, and then the charged particle goes to the electrode. Now, what happened? What happened when the charged particle goes to the electrode? When they goes to the electrode, that means the charge complete the circuit. Okay, it complete the circuit, so there will be a temporal current flowing in the circuit. Okay, because once the charges go to the electrode, then it enters the electrode and then it goes inside the circuit. All right, so it only happens temporarily. Temporarily, you have created a current, and that we call it as a pulse, right? P-U-L-S-E, electric pulse is like just a sudden rise in current. Okay, so that means when there's one emission, then you will create a pulse, one electric pulse. And this electric pulse pass through the, okay, it could be a speaker. If it's speaker, then this speaker will create a sound. It will create a sound like ta. Then you can hear this sound. Then you know, when you hear the sound, then you know one emission is, okay, there's one emission, okay, it's okay, there's one emission. So one emission, one sound, one tick. If got 4 emissions, then you will hear 4 tick. Tak, 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 tak. Then you can count 1, 2, 3, 4 in 1 minute. Okay, usually we count emission, we count it in emission per minute. Per second is too fast already. We put it in per minute. Okay. Now, so this is how the GM tube detect radioactive sources. So when you point to anything, and then you hear, is there sound? If there's sound, that means that source is giving out radiation. Okay. Do we know do we know whether it's alpha, beta, or gamma? Now, the thing is, the GM tube cannot tell whether it is alpha, gamma, or beta. It cannot tell. It can only tell how many emissions, because you can only hear the sound, but you don't know whether it's alpha, beta, or gamma. Because any one of these three, they can ionize. They are all ionizing radiation. So not only alpha can ionize, gamma also can ionize, but not as strong as alpha. So the sound that you're hearing, it could be alpha, it could be beta, or it could be gamma, but we are not able to tell it using the GM tube. If we want to know, whether it's alpha, beta, or gamma, then we have to use a different instrument. Okay, we cannot use the GM tube. The GM tube only let you detect whether the source is radioactive or not. Okay, you may have seen this in the movies, right? They point the detector to, like, they go to a like an area, okay, a place, they point it to the soil, and then they hear like tak, 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 something like that. Okay, that is the GM tube. Okay, so that is how it works. Now, if your radioactive source it can be like a rock, because a rock is also radioactive, but not at the dangerous level. It's very, very low emissions, because rock contain minerals. Okay, rock are found on the earth crust. It contains minerals. What are minerals? Minerals like naturally occurring element, right? Element that found in your periodic table, they are naturally occurring. So rock contains minerals, many types of minerals, not just one type, many types of minerals. And some minerals are radioactive. Okay, some minerals are radioactive. They can give out radiation, yeah, like this. So, but the radiation is not that high. It's about like 2 emissions per minute. That is considered normal for rock. 2 or 3 emissions per minute. So if you point it to the rock, any radioactive rock contain mineral, then you will hear the sound as well. If you're talking about like 200 emissions per minute, that is considered very high already. This is considered high already. A few hundreds or a few thousands, that is not from natural, like not from the rock already. That is from like other radioactive sources. The dose is quite high already. If 200 emission, it can cause danger to the living organs. So normal 2 emission, they are very normal. So actually, there are all kinds of radiations in our surrounding. Okay, surrounding, you got all kinds of radiation, but we don't see it, right? We don't know. Okay, even the soil, not only rock, soil. Okay, soil also contains radiations. They give out radiation, okay, but very low dosage. All right, so what is the function of the GM tube again? Okay, this is the GM tube. You need to be able to describe sometimes they will ask how does this work, and what is this, the function of this, the mica window, all that. All right, so the function of the GM tube, remember, is to detect. You only use to detect the presence of radioactive substances. Okay. So if no emission, there will be no sound created because the circuit is disconnected. So 1 emission, 1 pulse. Okay. All right. Let's go to the next page. You can take a screenshot of this if you want. We go to the next one. Okay, a picture of the GM tube looks like this. Okay, you can see this. This is the meter. Okay, you can see the count per second. Okay, this is in per second. You can see the rate meter here. And what you're seeing just now in the previous diagram, the tube, remember the tube, is this one. You see the cylinder, the black cylinder, this one? Yeah, this is the tube that you see just now. Okay, what is inside the tube is the electrode and the mica window, all that, right? So where's the mica window? Over here, this one. Over here. So you point this one to the source that you want to detect. Okay, then the rate meter, it counts the emission per second. Okay, example 9. Let us look at one calculation of the GM tube. Okay, when a radioactive substance is placed in front of a GM tube, the rate meter records 200 count per second. And after 24 minutes, the reading of the rate meter drops to 42 count per second. When the radioactive substance is removed, the GM tube still records a background radiation of 20 count per second. Determine the half-life of the radioactive substance. Okay, first let's talk about background radiation. What is background radiation? Background radiation is radiation from our surrounding. Like I mentioned just now, rocks, soil, they give radiation, right? So all this, they are considered one type of background radiation. Okay, you have two types of background radiation. One type is from the outer space that we call the cosmic radiation. And another type is the radiation from the earth itself, okay, from the soil of the earth. So we have cosmic radiation and also the internal radiation, which is from the earth. Even human also give out radiation in the form of heat, infrared, okay, that is also radiation. So radiation is just EM, electromagnetic waves. So what is really cosmic radiation? Cosmic radiation is radiation from outer space. Actually, the scientists, right, they don't know what is it until now. They don't know where does it come from. Okay, they just know that they detect a lot of radiation from outer space, from everywhere. Okay, from everywhere, until they are unable to find where is the source coming from. Okay, where is the source of the radiation? Because it comes from every direction. Okay, it comes from every direction. So they're unable to determine where is the source. Okay, so the source of the cosmic radiation remains unknown up to this day. But of course, they have a guess. They have a guess that they said, okay, this cosmic radiation, they all maybe it's from the star, okay, from the star, from the sun, okay, from galaxies, all that. Okay, they come from that. Okay, so the thing is, in outer space, there are many types of radiation. Microwave, okay, microwave. So it's like the how do you say that? There's a word for this one. Cosmic microwave background. You may have seen this cosmic microwave background. Okay, because in outer space, they detect a lot of microwave. They detect a lot of microwave. They believe that this microwave is actually from very, very long time ago. Like when the universe is still at the baby stage. Okay, it's growing, right? So when the universe is still at its baby stage, they give out this kind of radiation, and this radiation travels so far until it reaches our Earth today, and we detect it as cosmic radiation, microwave. Okay, so the bottom line is the radiation is from everywhere in the outer space. That is for cosmic radiation. Okay, and then we have another type of radiation is we call the internal. Actually, they don't really have a word for this. I mean, they have a word for this, but I'll just call it internal radiation. You get a point. Okay, that is the radiation from the earth. Okay, from the earth, from the soil, from the rocks, from your surrounding. That is all background radiations. Understand? Okay, so now this GM tube, the thing is, when you take the GM tube, right, you point it to the source that you want to detect. Not only you are detecting the emission from the source, you are also detecting the background radiation. Okay, because background radiation from the rock, from the soil, they can also be detected by the GM tube. So sometimes the reading that you get from the GM tube is the background radiation plus the radiation from the substance that you are detecting. Okay, now how do we solve these questions? Determine the half-life of the radioactive substance. Now, to do this, if you are faced with this type of questions with background radiations, right? You can do like this. I'm going to do 3 columns. First is my GM tube reading, and then I have the sample. That is the substance, and then I have the background radiation, BG. Okay. Now, at first, the rate meter detect 200 count per second. Okay, I'm going to write down here 200 count per second. They are all in count per second unit. Okay, so if the GM tube detect 200, does it mean that the sample is giving 200? Not necessarily, because here we got background radiation, right? So you have to be careful with this one. How much is the background radiation? 20 count per second. So meaning that here we have 20. And if the background radiation is 20, then how much is from the sample? 180. That is the radiation emission from the sample itself. Okay, now then we move to the next half-life. Next half-life, which one is decreasing to half the value? Okay, remember the sample is the one that is decaying. So 180 you divide by 2 goes down to 90. Okay, now common mistakes made by students is that they take the GM reading 200, they drop this to 100. This is not correct because this is the GM reading. The one that is decaying is a sample, is the substance that is decaying. Okay, so we drop this to 90, not this one. Okay, right, so sample is 90. What about the background radiation? The background radiation does not change, guys. It remains the same. It remains the same as 20 because the background radiation will not reduce by half. Only the sample is reduced by half. Okay, so the background radiation will remain as 20, and that gives your GM reading after 1 half-life is 110. Okay, 110. Now, continue. 1 more half-life. Then this drops to 45. This remains 20. And then the reading of the GM, 65. We keep doing this until, what is the question 1? The reading of the rate meter drops to 42 counts. Okay, we keep doing that until the GM drops to 42 counts. Okay, so 45, again, we drop it to 22.5. This one is 20 also. So 42.5. We stop here, right? 42 count per second. Okay, this approximate estimate, same. Right, so we stop here. Now, how many half-lives? 1 half-life, 2 half-life, and 3 half-lives. So from 200 down to 42.5, that is 3 half-lives. So the sample has gone through 3 half-life of decay. We write it as 3t half equals to how many minutes? This one from 200 to 42.5. It says in the question, right? After 24 minutes, the reading drops to 42. So meaning that from here to here is 24 minutes. So 3 half-life equals to 24 minutes. T half equals to 24 divided by 3, 8 minutes. So the half-life of the sample is 8 minutes. Okay, we look at next question. Okay, one more example here. The table shows the record of activity of a radioactive specimen in a period of 400 minutes. Predict the possible value of X. Okay, meaning that you want to find X in the units of count per second. Okay, from here we can see activity 482 down to 237. That's half of it, right? So that's one half-life. 237 down to 121. Again, another half-life. Okay, now from here, you can see look at the timer, 0 to 80. 0 to 80, this is 80 minutes different, and 80 to 160, that is also 80 minutes. 160 to 320. How many minutes here are between 160 and 320? That is 160 minutes, right? That means actually from 160 to 320, there are 2 half-lives. Okay, because sometimes they give you like this, it's like one, suddenly they jump like from 80, suddenly 160. So you can split it into 2 half-lives. Okay, so actually you can do like this. So I'm going to draw it out, 482 down to 237 down to 121, and then half of this, again, it is 60, then only 30, then only 15. Okay, so 80 minute, 80 minute, 80 minute, and 80 minute, 80 minute. Okay, so from this row number 3 and number 4, there are 2 half-life there. So be careful. You can divide it. You get 60 and 30. So which one is the X? Okay, which one is the X? X is the 30. Okay, 30 count per second. Because the time is 320, right? So 1, 2, 3, 4. It should be 4 half-lives. You get 320 minutes. So meaning that X is the 30 count per second. 30 count per second. That is my answer. Sometimes when you take half of it, it's not exactly half, but you can kind of take approximate values. Right, we go to the next one. Okay, that is for GM tube. Now we look at another device that we call the cloud chamber. Okay, cloud chamber. Okay, so this image shows the cloud chamber, and what is it used for? Now, GM tube is used to detect radioactive sources, but it cannot tell whether it's alpha, beta, or gamma. For a cloud chamber, it can tell whether it's alpha, beta, or gamma. Okay, so the function of a cloud chamber is to determine, to detect, to tell whether it's alpha, gamma, or beta. Okay, give me a second. 10 seconds. Finding my notes here. Where's my notes? Okay, never mind. Okay, never mind. Let's continue. Okay, so now a few things to note about cloud chamber. Okay, let's start from the bottom, the foam. Okay, the foam is used to support the dry ice. Okay, used to support the dry ice. So just to keep it attached to the metal plate. So here you have a metal plate. This is the metal plate. Okay, this is the metal plate. And just below the metal plate, the dry ice is touching it. So it's cooling the metal plate. Okay. So this dry ice is a very, very low temperature. It's about -78 degrees Celsius. Okay, very low temperature. Now, so the foam is used to support the dry ice. And what is the dry ice used for? The dry ice is used to cool the alcohol vapor until it is saturated. Okay, what does it mean by saturated? Okay, this here is typo here. Saturated. Okay, saturated. Now, saturated means if I say that the air is saturated, that means the air is at the tipping point of converting back to liquid. The air is at the tipping point of condensing, but not yet condenser. It almost want to condense back into liquid. Okay, that is saturated air. Right? So let me write down here. At the tipping point of condensing. But it is still vapor, it is still air. It hasn't condensed yet. So if you give a little bit of disturbance, okay, then it will start to condense. It is about to condense. That is, we say, saturated. So what is saturated here? You see the felt ring on top. This felt ring, what is this? This felt ring is soaked into alcohol. It is first dipped in alcohol. And the reason of doing that is because we want to supply alcohol vapor to the chamber. This felt ring is heated. Okay, they are heated on top here so that the alcohol vapor can come out. Okay, here is supply alcohol vapor into the chamber. Same for this one, the felt ring. Alcohol vapor is supplied, alcohol gas lah. Okay, in the chamber. Now, here the air, so inside this chamber, you have a mix of alcohol vapor and also air particles. Okay, you have a mixture of alcohol vapor and air particles. Now, the air close to the bottom, close to the plate, are cooled down by the dry ice. You have two regions of temperature. One is warmer up here, and it's cooler down here. Okay, when the alcohol vapor goes to the bottom, it will be cooled down. Okay, it will cool down to almost want to condensing, so it becomes saturated. Okay, let me repeat. The felt ring, it is heated to give out the alcohol vapor. Okay, it is still gas. And then the gas will come down close to the metal plate and be cooled by the dry ice. Okay, so meaning that you have very cold gases near the metal plate, and up here is very warm gases. Okay, now when they got cooler, they become very saturated. Okay, they become very saturated as they are cooled down, but they have not condensed yet. Now, what happened next? What happened next is I put a radioactive source here. You can see the radioactive source here. This is my radioactive source. And when the source gives out radiation, the radiation will ionize the saturated air. Okay, there will be ionization. Again, it will pull electron out, create ions from the air molecules, right? So you have charged molecules in the air. What happened is that this action create something like a disturbance to the air. Okay, because the air is so saturated that a little bit of disturbance can cause it to condense. I repeat again, because the air is so saturated that a little bit of disturbance, okay, like ionization, it can cause it to condense and become liquid droplets. Okay, so when the radiation is emitted, then the air will condense. And it condenses, it shows the trail of the radioactive substance. It's like the alpha particle, let's say you have an alpha particle goes in this direction. Okay, and then it causes the air along this direction, all the air along this direction, it causes it to condense and become water, become droplets. Okay, droplets. So what you will see, is that a track is formed along this line. Follow the direction of the alpha particle. If the alpha particle move here, then a cloud is formed along the path. So it's like you can see where is the alpha moving. Okay, what is this track? This track is basically clouds, like droplets, okay, like mist, okay, cloud, or you can say cloud or mist. It's like fog. Okay, it's like how the air goes up and then condense become clouds. It's the same thing as here. That's why we call it cloud chamber. Okay, it's called cloud chamber. So you will see like a cloud is forming, follow the path of the alpha particles. Okay, it can be alpha particle, it can be beta or even gamma particles. Okay, yeah. So this is how the track is formed. Sometimes they will ask you to explain. Explain how the track is formed. Okay, then you have to explain. Okay, because the saturated air, okay, saturated is about to condense, but once the emission come out, it disturb. There's a disturbance and it causes it to condense to become cloud. If there's no emission, right, will it condense? No. Okay, if there's no emission, then the air will stay as air. It won't condense. Only if there is emission, then it will condense. Later, I will show you a video, okay, for the cloud chamber, this one. Okay, so this is how it works. Now, the plastic lid on top is for you to look. You observe from the top, okay? You observe from the top, and then you can see the track forming here. The lamp here to provide some brightness, so you can see the track. Okay, the whole chamber inside is very dark, so you need some light source to see the tracks forming. Okay, so this is how it works. Now, how does it determine whether it is alpha, beta, or gamma? That's the question. Okay, if it's alpha particle, recall back, alpha particle, the ionizing power is the highest, correct? It's the highest ionizing power, followed by beta and followed by gamma. So you will see if the radioactive emission is alpha, then you will see the cloud is very thick, like this. Very thick cloud. Okay, so this is the trail forming, like this. Okay, very thick clouds trail form in the cloud chamber. You will see that. Why? Is because it is the most ionizing, right? It is the most ionizing. So there are the most cloud form, most ionizing, most, how do you say? The most number of droplets, yes, droplets form, okay? And also, for alpha, you can see it's not only it is thick, not only it is thick, it is also straight. Okay, use these two words to describe it. Thick and straight. Straight, why is it straight? Because when the alpha is moving in air, because of the high mass of alpha, the mass of alpha is quite high, is the nucleus of the helium, that it is hardly deflected. Okay, it is hardly deflected. So it goes in straight line like that. That is why it is straight. And why is it thick? It's thick is because its ionizing power is very high. Okay, so many droplets is formed here. So it forms a thick cloud. So it's the easiest to determine. When you see thick one, that's alpha, you know, okay? So one alpha come out, then you see one trace. Two alpha come out, you see two traces. Now, second one is the beta. Beta, right, is very light compared to alpha. How light is it? It's like 8,000 times lighter than alpha. Okay, about the mass of beta electron is very small. It's about 8,000 times lighter. So when electron is emitted, they are easily deflected. When they hit the air particle, they can change the path. So what you see is that it's kind of like a squiggly line like this. Like this. Okay, if you see this, then that means it is beta particle. It is very thin and kind of like curvy. Okay, thin and curved. Why is it thin? It's because the ionization power is not as high as the alpha, right? So it's thinner. And then its curve is because it hit the air particle and then it is deflected. Okay, so this you kind of see this wiggly line like that. All right, so for gamma, now for gamma is the least ionizing, right? So you see like disconnected, very small short traces and disconnected. Here I say short and disconnected. Okay, again, for the beta, you can also describe it as connected or continuous. Okay, the beta particle is continuous, the line is continuous, but the gamma is disconnected. Okay, this is the smallest one. It's very hard to see. Actually, you can still see it, but not as obvious as the beta and the alpha particle. So how do you identify? You look at the types of track that you see inside the cloud chamber. Okay, inside the cloud chamber. Now, you see the cloud form, because of ionization, right? Because the radiation, they have ionization power, they ionize the air and then causes the air to condense, right? So it's explained here, alcohol vapor condense to form liquid droplets around the ionized molecule, okay? So meaning that if you send electron inside the chamber, what would happen? Because electron also have charge, right? Electron can also ionize air, right? Like you put two metal plates inside, positive, negative. Okay, you connect to a circuit, or you put a Van der Graaf generator. You know what is a Van der Graaf generator? That you can, the one that you touch and then your hair stand up like that, right? The one that creates the charges. Okay, you generate charges and like send it inside the chamber, you can also see the condense, the air is condensing. Okay, later I'll show you a video right after this. Okay, what happened if I blast, like I blast electron inside. Okay, I blast electron inside. What will you see? Okay, so if I blast electron inside, you can also see that like a whole cloud of air condense into droplets. Okay, now let's move on to the clip. I'm going to show you a video, a very short video, not very long, very short video on the traces. Okay, how does it appear? How does it look? Let me share the video first. Just a second. Wait, I'm finding the video. Okay, I'm going to show you the first video first. The first video shows the traces formed in the cloud chamber. Okay, the traces formed in the cloud chamber. Okay, you should be able to see my video coming out. Let me adjust it a bit. Okay, do you see the video? If you don't see the video, let me know in the chat. You should be able to see the video right now. Let me make it bigger. Okay, let me play it. No sound. The video has no sound. Okay, you can see the whole thing, the glass, under the glass is inside the chamber. Okay, the chamber is inside the glass. So you can see the traces forming. It's kind of messy. So you can see all the thin one, they are the beta, right? You can hardly see gamma here. You see the thick one, the thick one are the alpha particles. You see, let me pause the video. Okay, do you see the thick one? This one, right? Okay, the thick one, this one, this one, this one. Okay, are the thick one. And the thinner one, the curvy one, they are the beta particles. I resume the video. Okay, from different angle. Okay, you see the thick traces suddenly come out. Those are the alpha. So one trace means one alpha being emitted. Where is the radioactive source? The radioactive source is in the chamber. It's from the side. Okay, this is a close-up view. Okay, so you're able to identify those are the beta particles, and then the thick ones, alpha particles. Okay, okay, let me stop the video. Okay, we have another video, that the one that I mentioned just now. What happens if I blast electron in the chamber? You will also see a cloud of mist, okay, showing the air condensed into droplets. Okay, because not only the radiation, not only alpha, beta, and gamma, even electron, because beta is also electron, right? So if I send electron in, the electron can also cause condensation. Okay, it can also form the clouds. And you can see from the video here, I'm sharing this second one. Okay. Okay, this one got sound one. If you're not hearing the sound, let me know. Let me test first. Wait.
Here we have a cloud chamber in active operation. If you look carefully, you can see the small trails of beta particles and the much thicker, whiter trails of.
Okay, let me replay it. I replay it. You should be seeing the video. Okay, yeah.
Here we have a cloud chamber in active operation. If you look carefully, you can see the small trails of beta particles and the much thicker, whiter trails of alpha particles. If you look towards the top, you can see that there is the end of a sharpened copper wire, which I've connected to a Van de Graaff generator on the outside. The negative electrode is connected to the pointed copper wire. The ground of the Van de Graaff generator is connected to the metal plate that forms the base of the cloud chamber. When I turn the Van de Graaff generator on, a stream of electrons will explode, literally, from the tip of the electrode inside the cloud chamber and create a cloud in the cloud chamber. Here's what it looks like. It's quite dramatic. Usually what a cloud chamber shows are individual tracks of individual particles. In this case, it's getting hit with millions of electrons all at once. Let's hit it again. And we'll short it out. Let things calm down. And we'll hit it again. What I'm doing is leaving the Van de Graaff generator on and periodically removing the shorting electrode from the top. And I'll remove it now. That's a burst of electrons striking the active layer of the cloud chamber and creating a cloud. Here's what happens if we leave it on and turn it on high.
Okay, so what you're seeing here is millions of electrons, right? Mentioned just now. If one
stream of electrons from the tip of the sharp electrode is blasting away at the active layer of the cloud chamber. That's not a stream of gas entering the cloud chamber, it's actually the electrons coming off the tip of the electrode.
Okay, so it says what just now? It says that those are not gases, right? Those are actually electrons. Okay, those are electrons that are coming out. So one electron, you will see one trace. If millions of electrons, then you see something like just now, okay? The whole cloud form. Okay, if one electron, then you only see one trace. Okay. Okay, let me go back to the video. Okay. Now, guys, I'm going to give you a 5-minute break. Sorry, not too long, 3 minutes break. Then we'll continue. Okay. Okay, I'll be back in 3 minutes. So we'll continue in 8:07. Okay, now we continue. Okay, so that is for the cloud chamber. And now we look at the next one. Okay, the next one is the spark chamber detector. Okay, so what is this used for? It can only detect alpha particles. Okay, now again, GM tube to detect radioactive. Cloud chamber, you can tell what is the radiation. And for spark chamber, only detect alpha. So this is the diagram, very simple arrangement. Basically, you have two terminals. One is the negative, one is the positive terminal. This thin wire is the positive terminal. And then you have the wire gauge, the negative terminal. And both are connected to very high voltage supply. Okay, very high voltage. Why high voltage? Is because it needs to attract the small molecules, the small ions, once the air is ionized. Okay, so it's high voltage supply. Now the thing is, where do I put my source? The source is here. I put the source here, and then you emit alpha particle. Okay, you give out alpha particle. That what happened to the alpha particle? It will ionize the air. Okay, ionize the air, so you have positive charge, and then you have negative charge. Okay, and this positive and negative charge, they will move to the terminal. Okay, so positive will move to the negative. Here it will go to the wire gauge, and then the negative charge will go to the thin wire, okay, to the positive. Why this one can only detect alpha? Because only alpha is strong enough to ionize the air here. Okay, so it cannot detect beta, because beta, right? If you put beta here, beta they are not strong enough to ionize the air and produce the spark. Okay, actually this one, a spark is produced when the alpha particle ionize the air. You get ions, and then when the ion move to the positive and negative terminal, they create a spark. That's why we call it a spark chamber. Okay, you will see a spark here, like a lightning. Okay, one spark means like one emission. Okay, you can see the spark here. The spark sounds like zzz, 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 something like that. Okay, so why high voltage? Is because it needs to attract the ions like that. So this is spark chamber detector, only detect alpha particles. We go to the next one. Okay, so we have the three detectors, and this is the last one. And actually, this one is portable, meaning that you can carry it. Actually, it's very small. It's about like 3 cm width and then 5 cm length. It's a badge, like a badge that you wear with you. You wear here. So it's called a film badge or a dosimeter. What is it? This is for the people who work at the nuclear power plant or any places that has radioactive emissions. Okay, so actually they wear it as a badge. Okay, they wear it on their shirt. Whenever they go to work, right, they have to wear it. And then after they finish work, they have to return it. Return this badge to the lab. Okay, and then the person in the lab will take the film badge and then they can analyze. Basically, what this film badge does is that it tells you how much you are exposed to radiation on that day. Okay, let's say you are a worker who works at the power plant, nuclear power plant. Okay, so you're not able to see radiations, right? You need something to detect it. So you wear the film badge. Okay, at the end of the day, you submit the film badge and then they can tell you, okay, how much you're exposed to radiation today. If you're exposed to very high radiation, then they can give you like off day, the next day, because you cannot be exposed too much, right? So they will give you like a holiday, something like that, an off day, uh, a paid leave, something like that. Okay, that's the good thing about it lah. But actually, there's bad side lah. The good thing is if you're exposed to huge radiation, right, you can get holidays, many holidays. Sometimes they get like the whole week off. Okay, but the bad thing is that usually, if you work at the radioactive places, right, it kind of affects the longevity. Okay, because some people, they cannot live up to 60 or 70 years old, and they die at like 40 something, is because of the radiation. Okay, they are the prolonged exposure to radiation. Okay, so that is the downside of it, right? That is why people who work at the nuclear power plant, they are very high pay. Okay, they are very high pay because they're risking their life. Okay, so the thing is they have to wear this film badge. Now, how does it detect the dose? You can see here there is a photographic film. It's kind of like a transparent glass, something like that. Not transparent, solid. Sorry, let me rephrase. It's like a light gray color. Okay, light gray color. You can see the glass behind this one. This is the photographic film. Okay, is the light gray color. Initially, it's light gray color. Now, what does it do? This photographic film, right? It is covered with this silver bromide. Okay, a chemical. It is coated with the silver bromide. Now, what it does is when there is radiation that falls on it, then it will turn dark color. Okay, it will turn dark color. Initially, it is light gray. When there's radiation falls on it, it will turn dark. Even light falls on it, also it will turn dark, right? But it is covered by something so that light cannot hit the photographic film. Okay, only the gamma or the beta is able to penetrate through. Okay, so it's covered by a certain coating. Okay, so that the light cannot fall on the photographic film. Right, so the thing is, the photographic film has this silver bromide. So whenever the gamma ray hit the film, then it will turn dark, or beta hit, it will turn dark. So by looking at the color changes, you know that you are exposed to radioactive. Okay, and then you can see here, you can see that your two filter, right? This is the lead filter, and this is the aluminum filter. And on top, there's no filter here. So you can look at the diagram. If the radiation are beta and gamma, then the top region will turn dark color. Okay, because both can pass through, right? There's no filter, they pass through, they hit the film, and then they causes the film to turn dark because of the reaction with the silver bromide. Okay, you can read here, the ionization effect by the radioactive rays will decompose silver bromide on the film, okay, and turns dark color. Now, the aluminum filter in the middle, it can block what? It can block the beta. Okay, the aluminum can block beta, but gamma it cannot block. Okay, you can see gamma can pass through here. So if you are exposed to, let's say, only beta particle, okay, if you are exposed to only beta particle, then your film badge only turns dark at the top, but at the middle and at the bottom, it stays light gray color. Okay, still it stays like initial color because the beta cannot pass through, okay, cannot pass through the filter. So it won't pass through the film. That is why you see light gray color at the bottom. Okay, and the last one is it can block lead, can block both gamma and and beta. So if you are exposed to gamma, let's say gamma particle comes, and then you'll see the batch turn dark color in the middle section and the upper section. Only the bottom section, it stays light gray color. Okay, so then you know if the middle turn dark, then it must be a gamma, because beta cannot pass through. So if it turns dark, then it must be gamma ray that it's exposed to. Okay, why there's no alpha? Maybe you wonder, where is the alpha? Why no alpha? Because alpha normally they are destroyed when they are emitted. The moment they come out, right, they are destroyed already. They don't have long lifespan. It's just like a few centimeters, they die already in air. Okay, so seldom you have alpha. Okay, seldom you have alpha passing through your body, unless like you swallow something like the radioactive substance that can give up alpha, then that can happen. Okay, so in air, alpha suddenly seldom they will pass through the body, because the lifespan is very short. Okay, that is why you see only gamma and beta here. Okay, so at the end of the workday, the worker, they surrender this one to the guy in the lab, and then the guy will do the analysis. Okay, how many doses that you are exposed today. Okay, so that is film batch. Film batch. It's very, very tiny, very small. Okay, so we have looked at total of 4: the GM tube, the cloud chamber, the spark chamber, and the film batch. Okay, all these are in your SPM syllabus. Okay, what time is it? Let me see, 8:20. Okay, it's almost I maybe take like 10 to 15 more minutes, and I'll give you exercises. Okay, so next one. All right, so we finished for all the detectors. Next one, we will look at the users. What are some of the users of radioisotope? Now, first thing, what is radioisotope? Radioisotope. Means that it is radioactive isotopes lah. Okay, radioactive isotopes. What is isotope again? Isotope is, for example, like sodium. You have sodium 23, and then you have sodium 24, right? So this is isotopes of sodium. Same proton, but different neutron number, okay? So sodium 23 is stable and sodium 24 is unstable. So sodium 24 is radioactive isotopes, and we short it as radioisotopes. Right, so what are some of the general, right? Okay, the general uses of radioisotope. The first one is in medicine. Okay, in the medical industry, it is used in scanning. Basically, they give you, for example, the scanning of the organs inside or any cancer cells are inside. They give you, first they inject the radioactive substance in your body. The injection, okay, it can be injection, or it can be they give you something to swallow. They give you something to swallow, and then that substance is actually radioactive, but the half-life of the substance is only about 8 hours. Okay, 8 hours of half-life. Meaning that in one day, 24 hours, it would have decay 3 half-lives, right? 3 half-life, and in one day, the dose become very small already, because after 3 half-life, the amount become very small already. Okay, so they let you swallow this one, a radioactive substance that has short half-life. Okay, and the reason is that when you swallow it, then the radioactive substance follow the digestive tract, right? and it can give out gamma rays, it can give out gammas, and then it can penetrate through your body. And then they use a detector outside. They use a detector outside to scan, okay, to create an image of your organs. Okay, so the image of the thyroid gland created from the gamma rays emitted here. Okay, and it shows some abnormal growth. Okay, you're able to visualize all this. They have a detector scanner. Okay, so first is that they inject the radioactive substance inside. So why we have to use like low half-life, small half-life, is because to minimize the dose. If you use like huge half-life, then long term, it can destroy your cells because the radioactive amount is too high already. So you have to use a small half-life, like 8 hours, like that. Okay, so 1 day or 2 days gone already. Okay, that is used for medical, the first one. Second one, it can also be used to kill cancer cell. Okay, also in the medical industry, kill cancer cell tumor. Okay, the developing cancer cell. So basically they focus the radiation on the tumor. Okay, and then you can see there are 3 positions here, right? Why 3 positions? Actually, this thing is like rotating. It's constantly moving. Okay, they cannot like stay still. It's because if they stay still, right, the gamma ray can destroy this region of the cell. Because not only it focuses on the not only it kills the tumor, right? Sometimes it can harm the cell nearby as well. Okay, so to prevent that from happening, okay, from damaging the cell too much, they have to move the source. Okay, so sometimes these cells are exposed and sometimes these cells are exposed. Sometimes it's like different regions of cells. Okay, so they don't only like focus on one area that causes the cell to damage. Okay, they go around in the position, they change position, but they remain focused on the tumor cell. They remain focused on the tumor cell. So the cell nearby maybe got damaged a little bit, okay, but not much. Okay, that is the second user to kill cancer cells. Now, next one, monitoring content of food. This is used in the industry, not medical industry, is the manufacturing, okay, all these industries. So this one, basically you have like, usually they use it for canned food. Because canned food is sealed, right? You cannot see inside. It's sealed already, you cannot see inside. So they have a canned food pass through the conveyor belt. And then they have a radioactive source at the bottom that shoots out radiation up. It shoots the radiation through the canned food here. And then if the content of the canned food is lower than what it should be, okay, the content is lower than it should be, then you will detect a high reading at the detector. Okay, the rate meter will show a very high reading, because if the content is very small, only a little content, then many radioactive radiation can pass through. It can pass through. So the rate meter reads a very high reading. Okay, so high reading will be recorded if the content is less than normal. So they know from the computer. All this is done using a computer. Okay, the computer will give instruction to whether to scrape it, to remove it, or to take it. All right. So if it's normal content like this, then the rate meter will detect very low radioactive reading, because since the content is more, right? So it can block more of the radiation. Okay, so less content, it blocks less. So high reading. Okay, so without looking at it, you can detect, okay, which one do I scrape it? Okay, that is monitoring the food content. And then next one is almost the same as the previous one. This is monitoring the thickness of the paper sheet. Okay, in manufacturing, like the steel sheet, you can see the thickness, you can determine the thickness of the steel sheet. Okay, so by passing through the radioactive, then we detect the amount of radioactive received at the rate meter. Okay, we are able to tell the thickness of the metal plate. So you can make sure that the thickness is uniform lah, so you don't get like very thick here and then you don't get very thin here. Okay, you can make sure it's uniform. Okay, the last one. Detecting underground leakage. Okay, underground leakage. Okay, this one is for underground pipe. Because if there's leakage in the underground pipe, you cannot see it, right? Because the water is still below the ground. It will not rise up to the ground. You still cannot see it. So how do you detect it? You use you use a GM tube. Okay, so what happened is that you move, you actually move this GM tube, you move across from left to right, like you sweep through, you move it across, and then if there's a leakage here, it will detect the radiation. Okay, first the water has to be added with a radioactive material. Okay, water added with radioactive sodium 24 here. So sodium 24 is radioactive, right? It's radioactive isotope. So it can emit radiation. So if there's a leakage here, then it can detect suddenly a very high dose of radiation. Okay, like you scan through the GM tube, something that, okay, you can detect very high dose at this region. Then you know there's a leakage. Okay, you know there's a leakage of pipe at this region here. Okay, so to detect the underground leakage using radioisotope. All these are the uses of radioisotopes. So we have discussed the detectors, 4 types of detectors, and also some of the uses of the radioisotopes. And that we will wrap it for today's lesson. The rest of the chapter, which are the mass or the nuclear energy, all that we will go through it next lesson. Okay, next week. So we will stop here. We still have half an hour. Okay, so I'll send you the practice exercises and you can do it in class. Now, the last practice from last week, if you have any questions, again, if any question, remember to ask, because if you don't ask, I don't know whether you understand or not. Okay, I don't know if you have problem. If you don't tell me, I don't know. Okay, so you have to reach out. Tell me if you not understand anything, any help you need. Okay, and make sure to finish all the exercise I give you. Okay, if you finish, if you follow and you do all the exercises, then SPM should be no problem for you. Okay, now your school test is a bit different because your school test always they take the UEC syllabus in. Okay, they do the UEC unless you want to go for UEC. Okay, but I see no point of learning the syllabus if you're only sitting for SPM. Okay, so meaning that in the school test you may get very low marks, but in the SPM you will get an A if you follow everything that I give you, all the exercises. Okay, because in the SPM many things that you learn will not come out. Okay, will not come out, especially the UEC syllabus, and they all won't come out. Okay, so the exercises, finish it every time you finish the lesson, so you remember. Okay, you remember, right? You remember, and then so when you revise, if you understand, when you revise, then it's very easy to pick up. It's very fast to pick up. Okay. Right, so we're going to stop here and I'll send you, take a break, and then I'll send you the exercises you can do in class. Okay, sometimes they will ask, if you look at the questions in the objective, sometimes the question will ask, what type of radiation is suitable to use in certain conditions like the detecting underground leakage. Okay, why we use sodium-24 here? We use sodium-24 here is because not only it has long half-life, about 15 hours. The half-life of sodium-24, about 15 hours, is quite long, but not too long, because if too long, if the half-life is too long, then it can release a lot of radiation that can harm the, if you drink the water, it can harm you because it can too high, the dose of radiation too high. Okay, so it can pose certain threat or danger if the half-life is too long. So it cannot be too long. So also it cannot be too short, right? If it's too short, then the moment you put it in, then the next day gone already. You cannot detect the leakage already. Okay, it has to be something that you can keep it in it for like a few days. Okay, 1 or 2 or 3 days, a few days, so that you can carry out the detection, okay, in time. So 15 hours is just nice. So sodium-24 uses a half-life of not too long and not too short. Okay, not too long and not too short. So in selecting the radioisotope, you have to choose the correct one lah. So they give you, like, for example, which one do you use for the detecting leakage? Is it the gamma? And then you have half-life of 6,000 years. This one, no, it's not too long already. If you put 6,000 years, then the water is like get polluted. Okay, cannot. So we use half-life as about like 15 hours. Okay, or it can be like a few hours, 8 hours, something like that. Okay, so in detecting leakage, usually is beta particle. Beta particle. Why we cannot use alpha for this one? Because alpha would be absorbed by the soil. Okay, alpha, they cannot penetrate. They have low penetration power, right? So the moment they come up here, they got absorbed by the soil, you cannot detect it. So usually it is either gamma or beta. Same as the detecting of the sheet, the plastic of the metal sheet. Okay, this one, can you use alpha? You cannot use alpha, right? Because alpha cannot pass through. So there's no detection here. So you have to use beta particle or gamma particle. Okay, so this one for the manufacturing, you can use longer half-life because you don't need to keep on changing it, keep on replacing it. Okay, you can use longer half-lives.